Loop quantum gravity is a theory that attempts to describe the quantum properties of the universe and gravity. It is also a theory of quantum spacetime because, according to general relativity, gravity is a manifestation of the geometry of spacetime. LQG is an attempt to merge quantum mechanics and general relativity. The main output of the theory is a physical picture of space where space is granular. The granularity is a direct consequence of the quantization. It has the same nature as the granularity of the photons in the quantum theory of electromagnetism and the discrete levels of the energy of the atoms. Here, it is space itself that is discrete. In other words, there is a minimum distance possible to travel through it. More precisely, space can be viewed as an extremely fine fabric or network, woven of finite loops. These networks of loops are called spin networks. The evolution of a spin network over time is called a spin foam. The predicted size of this structure is the Planck length, which is approximately 10⁻35 meters. According to the theory, there is no meaning to distance at scales smaller than the Planck scale. Therefore, LQG predicts that not just matter, but space itself, has an atomic structure. Today LQG is a vast area of research, developing in several directions, which involves about 30 research groups worldwide. They all share the basic physical assumptions and the mathematical description of quantum space. The full development of the theory is being pursued in two directions: the more traditional, canonical loop quantum gravity, and the newer covariant loop quantum gravity, more commonly called spin foam theory. Research into the physical consequences of the theory is proceeding in several directions. Among these, the most well-developed is the application of LQG to cosmology, called loop quantum cosmology. LQC applies LQG ideas to the study of the early universe and the physics of the Big Bang. Its most spectacular consequence is that the evolution of the universe can be continued beyond the Big Bang. The Big Bang appears thus to be replaced by a sort of cosmic Big Bounce. History. In 1986, Abhay Ashtekar reformulated Einstein's general relativity in a language closer to that of the rest of fundamental physics. Shortly after, Ted Jacobson and Lee Smolin realized that the formal equation of quantum gravity, called the Wheeler-DeWitt equation, admitted solutions labeled by loops when rewritten in the new Ashtekar variables. Carlo Rovelli and Lee Smolin defined a non-perturbative and background-independent quantum theory of gravity in terms of these loop solutions. George Pullin and Jerzy Lewandowski understood that the intersections of the loops are essential for the consistency of the theory, and the theory should be formulated in terms of intersecting loops, or graphs. In 1994, Rovelli and Smolin showed that the quantum operators of the theory associated to area and volume have a discrete spectrum, that is, geometry is quantized. This result defines an explicit basis of states of quantum geometry, which turned out to be labeled by Roger Penrose as spin networks, which are graphs labeled by spins. The canonical version of the dynamics was put on firm ground by Thomas Thiemann, who defined an anomaly-free Hamiltonian operator, showing the existence of a mathematically consistent background-independent theory. The covariant or spin foam version of the dynamics developed during several decades, and crystallized in 2008. From the joint work of research groups in France, Canada, UK, Poland, and Germany, lead to the definition of a family of transition amplitudes, which in the classical limit can be shown to be related to a family of truncations of general relativity. The finiteness of these amplitudes was proven in 2011. It requires the existence of a positive cosmological constant, and this is consistent with observed acceleration in the expansion of the universe, general covariance and background independence. In theoretical physics, general covariance is the invariance of the form of physical laws under arbitrary differentiable coordinate transformations. The essential idea is that coordinates are only artifices used in describing nature, and hence should play no role in the formulation of fundamental physical laws. A more significant requirement is the principle of general relativity that states that the laws of physics take the same form in all reference systems. This is a generalization of the principle of special relativity, which states that the laws of physics take the same form in all inertial frames. In mathematics, a diffeomorphism is an isomorphism in the category of smooth manifolds. It is an invertible function that maps one differentiable manifold to another, such that both the function and its inverse are smooth. These are the defining symmetry transformations of general relativity, since the theory is formulated only in terms of a differentiable manifold. In general relativity, general covariance is intimately related to diffeomorphism invariance. This symmetry is one of the defining features of the theory. However, it is a common misunderstanding that diffeomorphism invariance refers to the invariance of the physical predictions of a theory under arbitrary coordinate transformations. This isn't true, and in fact every physical theory is invariant under coordinate transformations this way. Diffeomorphisms, as mathematicians define them, correspond to something much more radical. Intuitively, a way they can be envisaged as simultaneously dragging all the physical fields over their differentiable manifold while staying in the same coordinate system. Diffeomorphisms are the true symmetry transformations of general relativity, and come about from the assertion that the formulation of the theory is based on a bare differentiable manifold, but not on any prior geometry. The theory is background independent. What is preserved under such transformations are the coincidences between the values the gravitational field take at such and such a place, and the values the matter fields take there. From these relationships one can form a notion of matter being located with respect to the gravitational field, or vice versa. This is what Einstein discovered, that physical entities are located with respect to one another only and not with respect to the spacetime manifold. As Carlo Rovelli puts it, no more fields on spacetime, just fields on fields. This is the true meaning of the saying. The stage disappears and becomes one of the actors. Space-time as a container, over which physics takes place, has no objective physical meaning, and instead the gravitational interaction is represented as just one of the fields forming the world. This is known as the relationless interpretation of space-time. The realization by Einstein that general relativity should be interpreted this way is the origin of his remark, "Beyond my wildest expectations." In LQG, this aspect of general relativity is taken seriously, and this symmetry is preserved by requiring that the physical states remain invariant under the generators of diffeomorphisms. The interpretation of this condition is well understood for purely spatial diffeomorphisms. However, the understanding of diffeomorphisms involving time is more subtle because it is related to dynamics and the so-called problem of time. In general relativity, a generally accepted calculational framework to account for this constraint has yet to be found. A plausible candidate for the quantum Hamiltonian constraint is the operator introduced by Thiemann. LQG is formally background independent. The equations of LQG are not embedded in, or dependent on, space and time. Instead, they are expected to give rise to space and time at distances which are large compared to the Planck length. The issue of background independence in LQG still has some unresolved subtleties. For example, some derivations require a fixed choice of the topology, while any consistent quantum theory of gravity should include topology change as a dynamical process. Constraints and the Poisson bracket algebra. The constraints of classical canonical general relativity in the Hamiltonian formulation of ordinary classical mechanics. The Poisson bracket is an important concept. A canonical coordinate system consists of canonical position and momentum variables that satisfy canonical Poisson bracket relations. where the Poisson bracket is given by for arbitrary phase space functions, and with the use of Poisson brackets, the Hamilton's equations can be rewritten as these equations describe a back-quote flow or orbit in phase space generated by the Hamiltonian. Given any phase space function, we have let us consider constrained systems, of which general relativity is an example. In a similar way, the Poisson bracket between a constraint and the phase space variables generates a flow along an orbit in phase space generated by the constraint. There are three types of constraints in Ashtaker's reformulation of classical general relativity. Gauss gauge constraints, the Gauss constraints. This represents an infinite number of constraints, one for each value of. These come about from re-expressing general relativity as an Yang-Mills type gauge theory. These infinite number of Gauss gauge constraints can be smeared with test fields with internal indices, which we demand vanish for any such function. These smeared constraints defined with respect to a suitable space of smearing functions give an equivalent description to the original constraints. In fact, Ashtaker's formulation may be thought of as ordinary Yang-Mills theory together with the following special constraints, resulting from diffeomorphism invariance, and a Hamiltonian that vanishes. The dynamics of such a theory are thus very different from that of ordinary Yang-Mills theory. Spatial diffeomorphisms constraints. The spatial diffeomorphism constraints can be smeared by the so-called shift functions to give an equivalent set of smeared spatial diffeomorphism constraints. These generate spatial diffeomorphisms along orbits defined by the shift function. These generate time diffeomorphisms along orbits defined by the lapse function. In Ashtaker formulation, the gauge field is the configuration variable and its conjugate momentum is the triad. The constraints are certain functions of these phase space variables. We consider the action of the constraints on arbitrary phase space functions. An important notion here is the Lie derivative, which is basically a derivative operation that infinitesimally shifts functions along some orbit with tangent vector. The Poisson bracket algebra of particular importance is the Poisson bracket algebra formed between the constraints themselves, as it completely determines the theory. In terms of the above smeared constraints, the constraint algebra amongst the Gauss law reads, where, and so we see that the Poisson bracket of two Gauss law is equivalent to a single Gauss law evaluated on the commutator of the smearings. The Poisson bracket amongst spatial diffeomorphisms constraints reads, and we see that its effect is to shift the smearing. The reason for this is that the smearing functions are not functions of the canonical variables, and so the spatial diffeomorphism does not generate diffeomorphisms on them. They do, however, generate diffeomorphisms on everything else. This is equivalent to leaving everything else fixed while shifting the smearing. The action of the spatial diffeomorphism on the Gauss law is, again, it shifts the test field. The Gauss law has vanishing Poisson bracket with the Hamiltonian constraint. The spatial diffeomorphism constraint with a Hamiltonian gives a Hamiltonian with its smearing shifted. Finally, the Poisson bracket of two Hamiltonians is a spatial diffeomorphism, whereas some phase space function, that is, it is a sum over infinitesimal spatial diffeomorphisms constraints where the coefficients of proportionality are not constants but have non-trivial phase space dependence. A Lie algebra with constraints is of the form where a constants. The above Poisson bracket algebra for general relativity does not form a true Lie algebra, as we have structure functions rather than structure constants for the Poisson bracket between two Hamiltonians. This leads to difficulties. Dirac observables. The constraints define a constraint surface in the original phase space. The gauge motions of the constraints apply to all phase space but have the feature that they leave the constraint surface where it is, and thus the orbit of a point in the hypersurface under gauge transformations will be an orbit entirely within it. Dirac observables are defined as phase space functions that Poisson commute with all the constraints when the constraint equations are imposed. That is, they are quantities defined on the constraint surface that are invariant under the gauge transformations of the theory. Then, solving only the constraint and determining the Dirac observables with respect to it leads us back to the ADM phase space with constraints. The dynamics of general relativity is generated by the constraints. It can be shown that 6 Einstein equations describing time evolution can be obtained by calculating the Poisson brackets of the three-metric and its conjugate momentum with a linear combination of the spatial Adithya Morphism and Hamiltonian constraint. The vanishing of the constraints, giving the physical phase space, are the 4 other Einstein equations.